Hello everybody, again we continue with problem number 4. This one will be pretty technical. So if alpha and beta are real roots of quadratic polynomials with integer coefficients, we need to prove that alpha plus beta is always a root of polynomial also with integer coefficients, not necessarily quadratic, but of degree no greater than 4. Which all this means will be shown immediately. So alpha and beta are roots of quadratic polynomials, not necessarily of the same polynomial. Actually, this will be this is not set, and I think that this is not even possible, or it's trivial. I don't know at the moment. But alpha is the root of one quadratic polynomial. Let's say like this: ax squared plus bx plus c, and beta is root of another quadratic polynomial like dx squared plus ex plus f. Actually, this means that this first polynomial can be written as a times x minus alpha and x minus another root of that polynomial, which will we denote like gamma. And this another polynomial which has a root beta can be decomposed at x minus beta. D is in front of x squared, so here d, and times x minus another second root, which will be denoted delta. What we know by equating coefficients or famous Viete formulas, that alpha plus gamma, the sum of the roots of the first polynomial, is actually equal a minus b over a. Alpha and gamma are not necessarily rational numbers, but this sum will be a rational number because coefficients a and b are integers, so minus b over a is a rational number. Also, alpha times gamma is a rational number because by Viete formula it is equal c over a, which is again a rational number. Similarly, from the second polynomial we have that beta plus delta is equal minus e over d, which is again rational number. And the product is actually equal to f over d, which is a rational number. And so we need to find a polynomial of degree of at most 4, which will have alpha plus beta as one root. So this polynomial should have one linear factor like x minus alpha minus beta. This should be 1. This should be one linear factor in the factorization of that polynomial. And now we will simply try to construct it. We will simply try to guess what are other three linear factors here. One will be x minus gamma minus delta, which is an obvious choice because we deal with alpha, beta, gamma, delta, and these formulas here. we now need to guess another two. We will actually try some modification. We will try x minus alpha, but not minus beta, but minus delta. Trying to use this connection between beta and delta, so we have minus beta here and minus delta here. And another one will be x minus gamma, like here, but not minus delta, but again minus beta. And so we will try to prove that this is a polynomial with rational coefficients, and if we multiply with the least common denominator, we will have a polynomial with integer coefficients, and one root will be exactly alpha plus beta because of this first linear factor here. So how to prove that this is the product of these four terms has rational coefficients? We will actually use these four formulas here obtained from Viete formulas, but it's not completely straightforward. It is some kind of calculation. If we multiply these first two factors here, what we obtain is the following. We obtain x squared minus linear term with x is actually alpha plus beta plus gamma plus delta times x, plus, and we have actually products like alpha gamma plus beta delta plus, I will use Latin names for these Greek letters, so alpha delta plus beta gamma. Okay, and what we know? We know that this is rational, not this, but but alpha plus gamma is rational. This is the first formula above. Beta plus delta is rational here. So we know that this is actually a rational number, a rational coefficient here. This is rational and this is rational. These two are also rational numbers. The only one we are not sure that only two terms which we are not sure that they are rationals are these two. So we have this as some polynomial with rational coefficients. I will denote it as Q2 of x, some quadratic polynomial with rational coefficients, plus last two terms which are alpha delta plus beta gamma. And now okay, and actually if we multiply these two, we again obtain, I will for a moment, in this product here we again obtain this guy here, but this is different. So we again obtain the same quadratic polynomial Q2 of x with rational coefficients, but last two terms are now alpha beta and gamma delta. And again, we don't know that this is rational and we don't know that this is rational. But we shall now multiply this and this. We will now multiply q2x, which we know that this is quadratic polynomial with rational coefficients, plus alpha delta plus beta gamma, times this second one, which is the same polynomial q2x, but plus alpha beta plus gamma delta. We will multiply all this and we will then prove that after multiplication all coefficients are rational, which will conclude the proof. So I shall need space for that multiplication. Okay. So what we obtain after this multiplication? Of course, this times this is actually q2 squared of x plus we obtain this plus this multiplied with this q2, so we obtain alpha delta plus beta gamma plus alpha beta plus gamma delta. This is multiplied by this q2 of x. Not necessarily this. So plus, and of course the last term is this times this, which is actually alpha delta plus beta gamma multiplied by alpha beta plus gamma delta. And now it's a technical calculation that this, we will now prove that this is equal to, this is a rational number. I need to prove this, and I will prove that this is a rational number. It's not obvious, I need to prove this. So let me show how to proceed with this. So I'm looking at this first term here. I will simply look at this first and the third term and put alpha in front of parentheses, obtaining alpha times beta plus delta, plus, and from the second and the last term I have common factor gamma, and again beta plus delta, and now I have common term here and here, and this is simply beta plus delta as one factor and alpha plus gamma as second factor. And we know from Viete formulas from before that this is rational number and this is rational number, and we have a product of two rational numbers. Now we need to prove that this second, this product on the right is also a rational number. If we multiply this by this, okay, let me see what is this. This is alpha squared beta delta plus, if we multiply this and this, is alpha gamma delta squared, okay, plus if we multiply this and this is alpha gamma beta squared, and finally if we multiply this and this is beta delta gamma squared. So we have common factor beta delta here and here, obtaining that this is beta delta times this plus this, so alpha squared plus gamma squared, plus, and from the second and the third term we have a common factor alpha gamma, which is multiplied by beta squared plus delta squared. Now from before we know, from Viete formulas, we know that this is a rational number and that this is a rational number. So we need to show that this is rational and that this is rational. But alpha squared times gamma squared is simply alpha plus gamma all squared minus 2 alpha gamma. We know that this is rational and this is rational, so it is a rational number. And similarly, beta squared plus delta squared is beta plus delta, which is rational, squared minus 2 beta delta, again using formulas from before, Viete's formulas, that we know that this is rational. So we are concluding the proof this way. So we really obtained the product of 4 linear factors, obtaining the polynomial with rational coefficients. If we multiply it with the least common denominator, we obtain the polynomial of degree of at most 4 with integer coefficients, and one root is as desired alpha plus beta. So thank you. It was a kind of technical, but this is a proof. See you in the next video soon.